Good morning, students. In today's class, we will learn about the concept of work, power, and energy. Now, this work in the physics is said to be done when a force displaces an object. So here, if we have an object of mass m, and if you apply a force in this direction, and this force displaces this object from this position to this position, then the work is said to be done. And say if S is the displacement of the object, that is from this point to this point, then the work done will be equal to F into S. So the product of the force into the displacement will give you the work done. And here the force has to be in the direction of the displacement to apply this formula. So this formula is applicable only if this force is in the direction of the displacement. So here force in this direction and the displacement is also in this direction. But here if the force is in a different direction from the displacement, suppose we applied a force in this direction, and here the displacement is in this direction. So the force in this direction and the displacement is in this direction. Okay, so this is the direction of the displacement. So here the force is not in the direction of the displacement. So here to calculate the work done, okay, we don't simply just multiply the force and the displacement. What we'll have to do is we'll have to take the dot product of the force and the displacement. So here in this case, the work done will be given as F dot S, where this F is the force and S is the displacement, both in vector form. So here work done is F dot S, and this is equal to, from definition of dot product, we have F dot S be equal to Fs of cos theta. So this is the general formula for calculating the work done, and this theta is the angle between the force and the displacement. So the displacement is in this direction. Remember, this is the displacement S and this is the force. So here F vector, S vector. So the work done is Fs cos theta. So now this is the work done, Fs cos theta, and the SI unit of work done is joules, denoted by capital J. So this is the SI unit of work done, or from the formula, the SI unit of this force is Newton, and the SI unit of displacement is meter. So the SI unit of work done can be given in terms of joule or Newton meter. So this is the same. So we can say that 1 Newton meter is equal to 1 joules. So this is the SI unit of work done. Now, depending upon this theta, work can be positive or negative or zero. That is, depending upon the direction of the force and displacement, the work done can be positive, negative, or zero. For example, to find these cases, let us say we have an object on the ground, say of mass m. So this is the ground. So if we displace the object, say, from the ground to a certain position here. Okay, so if we lift this object of mass m from the ground to this position, say by displacement S, and the force applied here is in this direction. So this is the force applied in the upward direction. So in this case, the work done in the displacing this object from this position to this position will be given as W is equal to F as the magnitude of the force, the magnitude of the displacement, cos, and in this case we can see that the force and the displacement is in the same direction, so the angle between them will be equal to 0, and cos of 0 is equal to 1. So the work done in this case will be positive. So this is the first case where the work done is positive. Now suppose if after lifting this object from the ground to this position, we again bring this object again from this position to the ground. Okay, so here instead of lifting it upwards, we bring this object from this position to the ground through the same displacement S. And when you carry an object, the force will always be upwards. Okay, so if you carry any object with you, then the force always acts in the upward direction. So here you can see that while displacing this object from this position to this position, the force is upwards and the displacement is downwards. So here the work done will be equal to Fs and cos of, in this case, the angle between the force and the displacement. So this is the force, this is the displacement, so the angle between them is 180 degree. So we have cos of 180 degree, and cos of 180 degree is minus 1. So here cos of 180 degree is minus 1, or we can write this minus 1 here. So we have minus F into S. So in the second case, the work done is negative. Okay, so when the force is in the upward direction, the displacement is in the downward direction, then the work done is negative. Then we come to the third case. The third case is when you just carry an object. Suppose, again, let's say we have a ground. Okay, this is the ground. Then if you just carry an object, any object, small object, on your head. Okay. Again here, if you carry anything with you, then the force that you applied will always be in the upward direction. So this is the force. Now if you carry this object from this position to this position, so this is the displacement of the object from this position to this position. So here you can see that the force, when you carry anything, the force is upwards. So here the force in this direction and the displacement is in this direction. So here the angle between the force and the displacement is 90 degrees. So hence the work done is equal to Fs cos of 90 degree. And cos of 90 degree is equal to 0. So here this will be 0. So F into S into 0. This will be equal to 0. So in this case, the third case, the work done is 0. So this happens when you carry anything with you, okay, without just carry it with you, and you displace that object by some displacement S. So this is the concept of work done. Remember that work is measured as the dot product of force and displacement, and we can have work to be positive, negative, or 0 depending upon the force and the displacement, the angle between the force and the displacement. Now next is the concept of power. So we know that work is said to be done if we displace an object by some displacement. And now power here, this is the rate of doing work per unit time. So that is the definition of power. The rate of doing work per unit time is called power. And power is usually denoted by this symbol P. and here we can have average power and instantaneous power. So the average power, this is equal to the the amount of work done, the small amount of work done, divided by the small amount of time taken for the work to be done. So upon displacing an object, suppose if we displace an object from this position, this is the mass. So here we have a object displaced from this position to this position. If the time taken for the displacement of this object from this position to this position is small, then the power will be large. So if this del t is small, then power will be large. So here power gives us the idea of how much work can be done in the given time. So if we say that if you have more power, then you can displace or you can perform the work faster. That is, you can displace the object faster. But if the power is less, then it will take time for the force to displace this object from this position to this position. So if your P power is large, then it will take a small amount of time to displace this object from this position to this position. Okay, that is, the work done will be fast. But if power is small, then it will take a very long time for you to displace the object from this position to this position. That is, it will take a long time for work to be done. So that is the concept of power. And in the instantaneous power can be calculated by taking the derivative of work done with respect to time. So dt of this W will give you power. And the SI unit of power, is watt. W-A-T-T. So this is the SI unit of power. Or from the given formula, the SI unit of power can be joules. The SI unit of this time is second. So the SI unit of power can be joules per second. Hence 1 joule per second will be equal to 1 watt. So 1 joule per second, this is equal to 1 watt. So these are the two SI unit of power. Now we come to the concept of energy. So we know that work is said to be done if we displace an object. Power is the rate of doing work per unit time. And now energy, this is defined as the capacity to do work. Okay, that is the definition of energy. The capacity to do work. And again, work, what is work? Work is said to be done if we displace an object. So we can say that energy is the capacity to displace an object by some amount of displacement. And there are two types of energy. One is kinetic energy and one is potential energy. So we have two types of energy. Remember, one is kinetic energy and number two is potential energy. So kinetic energy, this is the energy possessed by a body by virtue of its motion. So if an object is moving, with some velocity, then that object possesses a kinetic energy to displace another object. Suppose if we have two balls, of one of mass m1 and another one of mass m2, and say if m2 is at rest first and this m1 is moving with some velocity v, then this ball of mass m1 has the capacity to displace this object. Remember, this is at rest, so when this is in motion, it will collide with this ball of mass m2. Then upon collision, upon collision, if this M1 collides with M2, then upon collision M2 will be displaced by some amount. So upon collision M1 will usually change its velocity, and M2, this also will start moving with some velocity. So we say that this object which is moving has the capacity to displace this object by some displacement, by some amount of displacement. So here, if an object of mass m in general moves with a velocity v, then the kinetic energy will be given as half mv square. So this is the formula for kinetic energy, half mv square. Now in potential energy PE, this is defined as the energy possessed by a body by virtue of its change in position or configuration. So here we take, for example, an object of mass m on the ground, and if we displace this object by a displacement s in this direction, and here upon displacing the object from the ground, the force applied is in this direction. So here the force that you applied in displacing is in the upward direction. Now due to this change in position, there arise potential energy, that is an energy to displace this block of mass m from this position to this position. Okay, so this block of mass m has the capacity to displace itself from this position to this position. So this potential energy arises if work has to be done against an opposing force. So here the force you applied is in this direction. There is an opposing force which is the gravitational force, and that is downwards. Okay. And suppose this one, the displacement s, the magnitude of the displacement is given by h, the height from this point from the ground to this position. So this is the magnitude of displacement. So here you apply the force in the upward direction, and this force is applied against the gravitational force. Then only the concept of potential energy arises, if we perform work against some opposing force. So that if we stop applying this force, so if upon displacing the object to this position we stopped applying that force, then what will happen is that this block of mass m will fall to the ground, or it will displace itself from this position to this position. Okay, so here again, when you lift the object from this position to this position, you're changing the position, and that change in position against the opposing force gives rise to the potential energy stored in this object. So that if you stop applying the force in the upward direction, this object will fall to the ground through a displacement h. And the potential energy, this is given as force into displacement, simply the product of force into displacement. And in this case we see that the force is mg, mass into acceleration, g is the acceleration due to gravity, the magnitude of the displacement is h. So in this case we have the potential energy PE to be equal to mg h. Okay, so remember, in potential energy arises if work is done against an opposing force. If there is no opposing force, then the potential energy will not arise. Another example of this potential energy is due to a spring. So if we have a spring connected to a block of mass m, and if we displace this block of mass m in this direction, that is, if we apply a force in this direction and we displace this block of mass m by some displacement from here to here. Okay, so this is the displacement, and this is the force applied. And the force is applied against an opposing force set up in the spring. So there is an opposing force known as the restoring force set up in the spring. So if you stop applying the force, what will happen is that this block of mass M will come back to its original position. So if we stretch this block of mass M from this position to this position, we are applying a force. And if we stop applying that force, what will happen is that this block of mass M again will come back to this position. So in this case also, there is a potential energy stored up in this spring due to the work done against the restoring force set up in the spring. So remember, again here also, potential energy arises if work is done against an opposing restoring force set up in the spring. So that is the concept of kinetic energy and potential energy. These concepts are very important. We shall derive the law of conservation of mechanical energy using these two concepts, and the energy stored in the spring also will be found out using this concept.